You know, every time you watch a rocket tear through the sky, or you feel that pushback into your seat as a car accelerates, or you even just see an apple fall from a tree, you're watching the same fundamental law of the universe play out. It's a law so incredibly powerful, yet so elegant, that you can write it down with just 3 letters. Today, we're going to unpack one of the most important equations in all of science. F equals m. I mean, you've seen it everywhere, right? On t-shirts, in movies. It's practically a cultural icon. But this is so much more than just a formula. This is Isaac Newton's second law of motion, and it's essentially the blueprint for how things move, everything from the tiniest particles to the massive sweeping orbits of planets. So let's dive in and really get what this is all about. All right, to truly appreciate the power that's packed into this tiny equation, we've got to decode it first. We need to break its code. What do F, M, and A actually stand for? Let's take them one by one. Okay, first up is F for force. And right off the bat, we need to clear up a huge misconception. A lot of us think that force is what creates motion, but that's not quite right. Force is what changes motion. It's the push or the pull on an object that causes it to speed up, slow down, or even just change direction. Next, we've got M for mass. Now, this is super important. Mass is not the same thing as a weight. Mass is really a measure of an object's inertia. You can think of it as its built-in resistance to being pushed around. It's how stubborn an object is. The more mass something has, the harder you have to push to get it to accelerate. And finally, there's A for acceleration. And no, this isn't just about slamming on the gas pedal. Acceleration is any change in velocity. So yeah, that means speeding up, but it also means slowing down. That's just negative acceleration. And get this, it even includes turning a corner at a perfectly steady speed because you're changing your direction. So the real magic is seeing how these 3 things dance together. The law tells us that an object's acceleration is directly proportional to the force you apply, but inversely proportional to its mass. What does that actually mean? Well, it's pretty intuitive. If you kick a soccer ball, the harder you kick it, more force, the faster it's going to accelerate off your foot. Simple. But now imagine trying to apply that exact same kick to a giant truck. The truck has way, way more mass, so the same force is going to produce a tiny, barely noticeable acceleration. More force, more acceleration, more mass, less acceleration. It's that simple and that powerful. So for hundreds of years, F equals ma has been taught in every physics class as the second law. And look, for most everyday things, it works perfectly. But what if I told you that this famous little equation is actually just a special case, that there's a deeper, more fundamental principle hiding just beneath the surface? Yeah, let's peel back another layer of this onion. So you have to ask the question, is F equals ma really the whole story? Is that iconic equation the final word on motion? Well, as it turns out, the answer is no. Newton's original idea was actually even more profound. And here it is. This is the real deal. Newton's truer, more general law connects force not to acceleration directly, but to something called momentum. This says that force is equal to the rate of change of momentum over time. And P right there, that's momentum. It's just an object's mass multiplied by its velocity. This is how Newton really thought about it. The change in an object's momentum is equal to the total force you apply to it. Now, why is this version so much more powerful? Because it works even when an object's mass is changing. Think about a rocket. As it flies, it's burning tons of fuel, so it's constantly getting lighter. F equals ma can't really handle that, but this version, it describes it perfectly. So how do we get from this more complex-looking law back to our old friend, F equals ma? Well, let's just walk through it. We start with the general law. Force is the change in momentum over time. Then we substitute momentum with what it is, mass times velocity. Now here comes the most important step. If and only if we assume the mass of the object stays constant, we can pull that m out of the equation. And what are we left with? Mass times the rate of change of velocity, which is literally just the definition of acceleration. And boom, there it is. F equals ma emerges as a very common, but very specific, case of the bigger rule. You know, the impact of this law goes so far beyond a physics textbook. It didn't just change our equations, it fundamentally changed how we humans saw the entire universe and our place inside it. The true power of this law is the power of prediction. When Newton combined it with his law of gravity, it suddenly gave us the tools to solve problems that had mystified humanity for centuries, like calculating the exact elliptical orbits of the planets. It's the bedrock for engineering basically everything, from bridges that stand for centuries to the braking system in your car to guiding a spacecraft to land on Mars. For the very first time, the universe didn't just seem random, it seemed knowable. And that created a monumental shift in our worldview. I mean, think about it. Before Newton, the cosmos was this vast, mysterious place, maybe guided by unpredictable gods or spirits. But after Newton, the universe started to look like a magnificent, intricate clock. A machine, one that wasn't random or chaotic, but one that operated on clear, predictable mathematical laws that we could actually figure out. But, of course, science never, ever stands still. As revolutionary as his work was, even Newton's masterpiece had its limits. There were some tiny gravitational oddities out there, like the weird wobble in the orbit of the planet Mercury that his laws just couldn't quite explain. And it was in those tiny cracks that the next great revolution in physics would begin to grow. Which brings us to a final pretty cool thought. Was Newton's law the final answer in our quest to understand motion? Or was it actually the beginning of an even bigger journey? It gave us the solid foundation of classical mechanics, for sure, but it also, inadvertently, pointed the way toward the next chapter, to Einstein's theories of relativity, which would once again completely reshape our understanding of space, time, and the very fabric of the cosmos.